Assalamualaikum and hello everyone. You are with me, Miss Huda. For this video, we're going to look at the principle of moment. Without further ado, let's start. At the end of this lecture, the student should be able to define the types of forces acting on a structure, recognize the principle of lever system, and understand and calculate the moment of equilibrium. We're going to look at the structural forces. Structure are all around us, everywhere we go, everywhere we look. They come in all shapes and sizes. Some are made by people while others are natural. Structures provide us with shelter and protection. All structures have force acting on them. Types of forces. It can be defined as any cause that tends to alter the state of rest of a body or its state of uniform motion in a straight line. A force is acting that can cause a change in an object. A force is any push or pull, meaning that a force can be a pushing force or a force can be a pulling force. The interaction of forces occurs when there is a direct contact between bodies. Type of forces acting on structure. 1, we have the external force, and 2 is internal force. External force is a force outside the structure. For example, we have a gravity force, wind blowing, snow load, the weight of object or people on or within the structure. Structures are generally designed to withstand external force 2 or 3 times larger than the normal. For example, we have the CN Tower, which is designed to withstand wind speed up to 418 km per hour. And for internal force, external forces create internal forces within the structure. For example, we have the compression force, tension force, shear, bending, and torsion forces. All structure must be designed to withstand the forces it will face. Wrong structure design will equal to structure failure. However, if the building is too strong, it will waste the time and resources. Hence, it is very important to understand the forces that may encounter accordingly, especially when you are designing a building structure. Force formula is equal to mass times with the acceleration, or in this case, we are calculating for force of the building. For example, is going to be mass of the structure times with the gravity acceleration. Then we're going to get the value of in Newton or kilonewton, which is, we call it weight or force. As in the previous slide, we know there is interaction of forces occur when there is direct contact between bodies. For example, here we have the internal force, tension. The forces acting on the object pull from each other. The object is being stretched from either ends, which means that when there is a load that pulling down 250 Newton and the reaction that pulling up is 250 Newton, which means that this object is in the state of equilibrium. How about compression? The forces acting on the object act towards each other. The object is being squeezed or compressed. For example, here we have 200 kilonewton forces going down, and there is a reaction of 200 kilonewton force going up. Next is shear. The forces acting on the object cause part of the object to slide in relation to each other, which means that there is one force acting to the left and another force acting to the right, which cause the object to shear. Next is bending. The force acting on the object produce a bending effect. This action can also cause a sliding or shear. If you look at the object here, we have a beam and two support at each end. The forces that coming from above will produce a bending effect to the object, to the beam, and it can cause the beam to shear, which means that it will break into two. The last but not least is torsion. The forces acting on an object cause it to be twisted. As you can see, the object is twisted. This is the illustration for each internal forces. Compression, which will cause the object to compress, shorten. Tension will cause the object elongate. Bending will cause the object to bend. Torsion will cause the object to be twisted. And shear will cause the object to perhaps break. To get a better understanding on the compression and tension, let's look at the example here. We have computer desk. For example, there's a desk, and on the top of the desk, there is a monitor and also the PC and keyboard. We're going to look at what happened to the thigh, which is here. The thigh is in tension. As you can see, because of the weight of the monitor, it will pull the thigh down, which means that this thigh is in tension. Next, B, this is the strut. Due to the weight of the PC and the keyboard, the force or the weight of coming from both things above, it will pull the strut down, meaning that the strut is in compression. And for the rod here, supporting the PC and the table due to the weight of the monitor, the weight of the computer, it will pull this one down. Okay, so at this area, it will be in compression. However, this at the outside here, this will be in tension because of it will try to bend this to the other side, meaning that it will bend to C. It will bend like this, right? Because of the force that pulling it down. Therefore, D is in tension and while C is in compression. Next, we have another example. The bracket holding up the hanging basket is made of steel. It has been made by heating up the steel until red hot and then bending it at the 90 degrees. This one, yeah. What is the force exerting on the bracket at point A? So this one is the bracket. As you can see here, because of the weight of the pot, there's a pulling down forces, which means that here it will be in tension. What type of force is the chain under? This is obviously it is in tension because of the weight is pulling it down. What type of forces are the wires holding the plant pot under? This one also, it should be in tension. What force is acting on the wall at point B? Due to the weight of the pot and the bracket is supported by the wall, therefore the wall is under compression. As more weight is added to the plant pot, the bracket begins to bend too much. How could the bracket be strengthened? The bracket can be strengthened by, for example, we can add a strut here, which it can provide more support to the bracket. And to answer the question 6, how could the bracket be fixed to the wall? Use diagram to illustrate your answers. By using screw that be screwed to the wall using a wall plug. That is basically the answer for all example number 2, I think. Right, next we're going to look at the bridges and loops. The bridge below is a common type called a box girder bridge. Usually they are manufactured in the factory and transported to the site and dropped into position by a large crane. The triangular shapes gives the bridge immense strength, and for short spans, this type of bridge is very ideal. For example, if there is a vehicle, for example, a car that crossing the bridge, each members of the bridge will experience some type of force. And we can see that the member that the car rests on is under tensile force down here. And the top member is in compress because it will start to bend. These are common forces. First, we have static load versus the dynamic load. Static load is a static, that's not moving load. And for the dynamic load, it is a moving load. For example, here we have a man carrying books and he's moving. And we have internal resistance, pushing back, which is resisting, and tension, which is this two person is pulling a rope, I think. Therefore, the rope is in tension. And for this one, weight lifting, this person is lifting a weight. Therefore, the weight here from the load above, it will cause compression. How about another one, the shear force? One of the example is the application of scissor. When the scissor is crossing each other, the blade here, it is producing a shear force. You can even cut paper using this scissor. Another one is a torsion. This is the act of twisting. You can twist. For example, here you have ruler. You can twist a ruler. Then the ruler will have this twisted effect. Moving on to the next one is lever system. Lever system is a rigid bar, whether it is straight or curved, affected by effort force and resistance force, and it is that rotate around a fixed point called fulcrum. For example, here, in the middle here, this is fulcrum. The application of lever system we can see in the moment of forces. Moment of forces is the turning effect of a force. As in the picture, you can see, for example, this is the turning point. It can be the fulcrum, and the person is pushing up the rod. And the turning effect here, we call it as moment. And how about this one, the hammer? The turning point will be at the head of the hammer, which is the force or the effort coming from here. Or maybe here the crane, right? So the crane, the turning force, meaning that this load can move left and right. The turning point is here. Simple machine, lever. Simple machines are mechanical devices that are used to make work easier. A lever is a simple machine made of a rigid beam and a fulcrum. the effort, which is the input force, and the load, which is the output force, are applied to either end of the beam. The fulcrum is the point on which the beam pivots, meaning that you have the fulcrum at the center, and one side will be the load, and the other side will be the effort. When an effort is applied to one end of the lever, a load is applied at the other end of the lever. This will move a mass upward. Levers rely on torque for each operation. Torque is an amount of force required to cause an object to rotate around its axis, meaning it can rotate downwards or upwards. A lever provides mechanical advantage. Mechanical advantage refers to how much a simple machine multiplies an applied force. The location of the effort, load, and fulcrum will determine the type of lever and the amount of mechanical advantage the machine has. The farther the effort is away from the fulcrum, the easier it is to move the load. This is the formula to calculate the mechanical advantage, which is very simple. Effort we divide with load, or effort is distance from effort to fulcrum, and load is distance from load to the fulcrum. Mechanical advantage is equal to the ratio of the effort to the load as well as to the distance from the effort to the fulcrum to the distance from the load to the fulcrum. So you can see from the formula given here. There are three classes of lever, which is the first one we're going to look at is class 1. If the fulcrum is closer to the load, then less effort is needed to move the load a shorter distance. If the fulcrum is closer to the effort, then more effort is needed to move the load a greater distance. From the illustration, when the fulcrum is nearer to the load compared to the effort, lebih senang load tu nak bergerak tapi pendek je jarak dia. However, kalau fulcrum lebih dekat dengan effort, lebih jauh load tu boleh digerakkan. For example, you have the seesaw or teeter-totter, a car jack, and a crowbar are the all example of first class lever. First class lever very useful for lifting large load with little effort. For example, here we have the workman uses a trolley to move the large packing case. The fulcrum is the wheel. This is the load. This is the fulcrum, and the effort comes from the man. Class 2 lever. If the load is closer to the fulcrum than the effort, then less effort will be required to move the load. If the load is closer to the effort than the fulcrum, then more effort will be required to move the load. Maksudnya, if you look at the illustration, kalau load ni lebih dekat dengan fulcrum, meaning that less effort to lift the load. Kalau this load lebih dekat dengan effort, meaning it is much harder untuk move the load. The application of class 2 lever, for example, we have a wheelbarrow, which is the fulcrum, is the wheel, the load, and this is the effort. How about a bottle opener? The fulcrum, the load, and this is the effort. And then or also as the example, this is the fulcrum, the load, and this is the effort. We have another example for class 2 lever. The gardener used a wheelbarrow to lift tools and garden waste. The load is in the center of the wheelbarrow, meaning that the load is here. This is the effort, and this is the fulcrum. Last one, class 3 lever. If the fulcrum is closer to the load, then less effort is needed to move the load. If the fulcrum is closer to the effort, then the load will move a greater distance. In this type of class, the effort is located between the load and the fulcrum. What does this mean? Meaning that kalau fulcrum ni lebih dekat dengan load, meaning that load ni shorter distance jarak dia dengan load, jadi effort dia lebih kurang lah untuk lift the object. However, kalau fulcrum ni lebih dekat dengan effort, meaning shorter distance like this, okay, the load will move greater distance, meaning you can lift it up more lah, lebih banyak greater distance. The application of class 3 lever, for example, we have a pair of tweezers, a swinging baseball bat, or using your arm to lift something are example of third class levers. These levers are useful for making precise movement if the fulcrum is closer to the effort. For example, the fulcrum, using the hands here and the effort, then the load will move greater distance. The fisherman catches the fish, which becomes the load at the end of the lever, meaning that here, this is the fulcrum, this is the effort, and here this is the load. Next, we look at the moment of equilibrium. This is the principle which we have the condition of equilibrium. As we know, whatever goes up will go down. Whatever going to right will go to the left, and whatever they're rotating counterclockwise will rotate clockwise. This is equilibrium. When there is a force moving upwards, then there should be a downward force. This is the state of equilibrium. When the force going to the right, there will be a counter force to the left. This is also equilibrium. And when there is a moment anti-clockwise, there should be another clockwise moment to counteract. Then there is the state of equilibrium. The illustration shows more on what does it mean with the principle of moment equilibrium. It clearly shows a state of equilibrium. The cars on either side of the seesaw are exactly the same in weight and height. In fact, they are the same model. It's just a different color. As a result, the seesaw stay level. The center of the seesaw is called fulcrum, and this is where the beam that the car rests on tilt backwards and forwards. However, because of it is in a state of equilibrium, they will remain completely still. The weight of the cars is called effort. If an extra car is added, let me draw another car here, to the right-hand side, then the seesaw will turn in a clockwise direction. It is called an clockwise moment. Alternatively, if more cars are added to the left-hand side, the seesaw will turn in anti-clockwise direction. This is called an anti-clockwise moment. If the seesaw is to be in equilibrium, the counterclockwise moment must equal to the anti-clockwise moment. The seesaw is back in equilibrium because of the second car has been added to the left-hand side. Therefore, samalah kanan dan kiri. It is in a state of equilibrium. To call this in a state of equilibrium, provided that the distance of both sides is the same. If I put here 2 meter, then this one should be 2 meter. If it is a different distance, the system here is not in a state of equilibrium. Therefore, the beam is not in balance. Measurements of moments. The effect of the forces resulted in the direction in which the body turns or tends to turn around a given point, which means, for example, the fulcrum. A moment is obtained by multiplying force by a distance. As you can see from the example of the car, even if the car is at the same model, just a different color, on the top of the beam or seesaw, and there's a fulcrum below, If the distance, as I mentioned, is different, it will affect the equilibrium. That's why we have to measure the distance in the equation. Moments are expressed in force length unit, such as Newton meter, kilonewton meter, Newton millimeter. The formula is going to be force times distance, which is the force whether it is kilonewton or Newton, on the distance meter or millimeter. The condition of equilibrium. Find the clockwise and anti-clockwise in the figure. In the figure, the fulcrum is the reference point. Every time that you want to calculate for moment, there will be the reference point. Because we want to know the turning of moment to the reference point. You have a force of 70 Newton here. So when you want to calculate the force, we know that moment is equal to force times distance. The force is 75 Newton. The force is going down. And the reference point will be the fulcrum. The distance is 300 mm. The distance should be 90 degrees from the direction of the force. Meaning if the direction going down like this, the horizontal distance that you should include in your calculation. In this case, the force will turn counterclockwise and 45 Newton will turn counterclockwise. How about 150 Newton? It will turn clockwise and 30 Newton will turn clockwise. Support and connection and jointing. Structural systems transfer their loads through a series of elements to the ground. This is accomplished by designing the joining of the elements at their intersections. Each connection is designed so that it can transfer or support a specific type of load or loading conditions. The conditions at each of the support greatly influence the behavior of the element, which make up each structural system. For example, structural steel system, the connections will be whether it's welded, bolted, or riveted. For precast concrete system, it might be a combination of few techniques such as steel plate, dowel, rebar, and many others. For timber, nails, bolts, or glue. The three common types of connection which join a built structure to the foundation are roller, pin, and fixed support. A fourth type that it is not really often used in the building structure is known as simple support. This is often idealized as the frictional surface. However, this is not very tak dipakai lah dalam building structure. All these supports can be located anywhere along a structural element. They are found at the ends, midpoints, or at any other intermediate points. Doesn't matter. The type of support connection determines the type of load that the support can resist. The support type also has a great effect on the load-bearing capacity of each element and therefore the system. The fixed support, it is most rigid type of support. It constrains the members in all translations and rotation. It does not allow joint to rotate. For example, the application it is column in concrete. Usually, it will be represented as this. And the support reaction, there will be a moment because it won't allow rotation. Therefore, it needs to resist moment. It don't allow movement vertically or horizontally, which means that it must resist horizontal force and it must resist vertical force. Second most common is pin support. A pin support can resist both vertical and horizontal forces. Type of support that allows the member to rotate. Therefore, it can't resist moment because it allows rotation. However, it must resist vertical and horizontal forces. Therefore, there is a reaction vertically and reaction horizontally. And this is what it represents. For roller support, it must be able to resist vertical force, which is the y direction, but not horizontal force, the x direction. It also allows rotation, which means it don't have moment since it allows rotation, and it allows movement horizontally, which means that there will be no horizontal reaction. However, there are vertical force since it must able to resist the vertical force, which means that there is reaction vertically. And this is what roller support represents. Next is SI units. So before we start the calculation, you must know how to do the conversion of units. And we're going to apply the SI units as it is a system that used widely except in the US. It comprises a coherent system of units of measurement built on 7 base units. It is intended to be evolving system, so prefixes and units are created and unit definition are modified through international agreement as the technology of measurement progresses and the precision of measurement improves. Here are example of unit conversion. So I think that most of you dah tahu. Perhaps this is the one that maybe you have to pay more attention, which is 1 kilogram equal to 10 Newton. Why? Right? Because of if you want to convert 1 kilogram, this is the mass. But when you want to convert it into Newton, which is the weight or the force, Newton is a force or weight. You have to times with the gravity acceleration, which is 10 meter per second power of 2. You will get 1 kilogram. You will get 10 kilogram meter per second power of 2, which is equal to 10 Newton. Let's try this. Calculate the volume of cube with dimension of 2 meter times 2 meter times 2 meter. So you just times all, then you will get 8 meter cube. If the density of the cube is 1000 kilogram per meter cube, you need to calculate the mass of cube. To calculate the mass of cube, you use this value, which is, it says that 1 meter cube is equal to 1000 kilogram. However, in your case, it is 8 meter cube. Therefore, you have to times with 8. You will get 8,000 kilogram. Convert the mass of cube to weight in Newton. The 8,000 kilogram, you need to convert into Newton, which means weight. You just times with the gravity acceleration. Therefore, you will get 80,000 kilogram meter per second power of 2, which is equal to 80,000 Newton. And convert the weight of cube to Newton. Bahagi saja dengan 1000, then you will get kilonewton. Thank you.